All right, so here's a quick synopsis of those four graphs. We have them all graphed on one coordinate plane here, and there is the 1/2 raised to the x, 1/3 raised to the x, 3 raised to the x, and 2 raised to the x. You can see the nice symmetry between those whose b values are just reciprocals. And you can also see that they are all going through one point. They are all going to have a y-intercept right there at 1. So let me take a moment to talk about some just characteristics of exponential functions. Anytime you take b and raise it to the x value of 0, well, anything raised to the x is going to be 1, no matter what your value of b is. And this is what generates a y-intercept. Because the x value is 0, the output is always 1. That is the y-intercept for our exponential functions of the form y equals b to the x. Also, remember we looked at those values as they got really far out, and they were extremely small. They were like 0.00000000003, but they didn't actually reach 0. The graph approaches the x-axis, but it doesn't touch it. This line that the graph is approaching but never intersects is called the asymptote. It's a new term we're going to use a lot when discussing exponential functions. When our b values are greater than 1, those functions are going to increase as your x values increase. And when you had those fractions, those like 1/2 and 1/3 values between 0 and 1, the value of your y is going to decrease as your x values increase. So those are just some characteristics that we wanted to clear up. There is a formula that was introduced in the objectives called the compound interest formula. Notice that this formula has the exponent value of n to the t. So this is an exponential function. Let me explain what each of those letters means. The A is the account balance after t number of years. The P is going to be the principal amount or the initial amount invested. The R is the interest rate, and you would need to express that as a decimal. And the N is the number of times that you are going to see the account be compounded in a year. How many times the interest rate is applied. So let's look at this in an example together. Mr. Malden invests $10,000 into a CD, which is like a savings option that banks sometimes have, where you can put them in, but you cannot take out the money for a certain number of years is usually what it is. And this CD earns 3% interest compounded daily. So we want to write an exponential function modeling the value of his investment, and then use that function to find the value of the account in 25 years, which is when he's going to retire. So let's get started. We're going to substitute in the principal, the interest rate, the number, and the number of compoundings into our formula. That would look like 10,000, and then in parentheses, 1 plus our rate, which 3% is expressed as 0.03. That's over 365 because it is compounded daily. And how many days are there in a year? 365. And it's raised to the 365 times t. T is our independent variable. T is what's going to really cause a lot of changes as that T value increases. So in part B, we're going to evaluate this at 25 because it is 25 years later. When you plug that all into your calculator, make sure that you first multiply 365 times 25. Otherwise, you could have a slight error when you type that in. It should give you $21,169.35. So that is quite a beautiful profit that he's made. It's just a little bit over doubled in those 25 years, thanks to this wonderful exponential growth function. And we're actually going to look at what we would need to do to reach our investment goals for retirement together in class. So I hope that you all look forward to that, and I will see you later.